Welcome back to this next video in which we are discussing splitting fields. Okay, so in this next video what we're going to take on is the problem of proving that a splitting field for a certain polynomial over an initial field capital F is unique. Okay, now what do I mean by that? I mean that if you generate a splitting field for a polynomial over a certain field, there is only one answer you can get, okay? Or at least if you do get two different answers, they will be isomorphic to each other. The only difference between them will be that you've used different symbols, okay? And this is why we can talk about the splitting field for a polynomial over a field capital F, because there is only one. There aren't multiple truly different splitting fields that are truly different algebraically from one another. The only difference between two different splitting fields of a polynomial over a certain field is that you've used different symbols. And of course that's trivial, that's man-made. Okay, that's not an actual proper algebraic difference between the two. Okay, so that's what we're going to take on in this video. Now, what we're going to do is we're going to prove a slightly more generalized theorem than that, and I hope it will be very obvious that if you just make the theorem a little bit more specific, it will indeed prove the uniqueness of the splitting field for a polynomial over a field. Okay, so let me state this theorem, and it's a long theorem to state, but I hope that once we've actually understood what this theorem is going to, well, what it's saying, we will be able to see very easily that by proving this, we prove that splitting fields are unique. Okay, right, so here comes the theorem that we're going to spend the rest of this video trying to prove then. Okay, so what we're going to start off with then is two fields that are going to be isomorphic to one another. Okay, so we're going to start off with a field capital F and another field capital F prime. So this theorem is absolutely going to be covered with primes, okay? Everything pertaining to this one will be unprimed and everything pertaining to this one will be primed, okay? And you're just going to have to get used to that. Okay, so we've got these two fields that we're starting off with, F and F prime, that are isomorphic to one another. Okay, so there will exist a nice mapping between the two, an isomorphism between the two here. And I'll denote this like so. We'll call it phi, and it's going to be a mapping from F to F prime that's going to be an isomorphism. And I know I've never used this notation before, but a way that people often show that a mapping is an isomorphism is they put a little squiggle above the arrow here. Okay, just like the equals here has got a little squiggle above it to show isomorphism. Okay, so we can find an isomorphism between these two fields. Now let me just remind you, in case you've forgotten, of exactly what an isomorphism and two fields being isomorphic to one another actually means. So remember, these two fields being isomorphic to one another means that actually they're not that different at all. Okay, the only difference between them is that you've used different symbols. Okay, and indeed, if you took this one and rubbed all the symbols out and replaced them with symbols in this one, okay, and indeed went to the addition and multiplication tables on this structure here, on this field, and did the same there, rubbed out all of the symbols and replaced them with the symbol they're being replaced with, you could turn this one into this one. And indeed, that's what an isomorphism actually is. It is telling you how to rub out the symbols here and what to replace them with from here. Okay, and if you were to follow the instructions that this isomorphism gives you and apply it and rub out all the symbols in the addition and multiplication table for this one and replace them as the isomorphism commands with the symbols in this one, it would turn the addition and multiplication table here into the addition and multiplication table here. So truly, the only difference between these is that you've used different symbols. That is what it means for these two to be isomorphic. Okay, so of course the symbols don't matter. What we're interested in is the actual algebraic structure. Okay, the symbols are man-made. They're just what did someone long ago choose to use as the symbols for these. Okay, that's not important. What's important is the core algebraic structure. That's the God-given bit, if you like, rather than the man-made bit. Okay, right, so we've got two fields here that are isomorphic to one another. Okay, and firstly, I just need to go through a whole bunch of setup to actually state this theorem. So you be aware that I've got to now say loads of things before I can actually state what the claim of this theorem is. Okay, so once you've got an isomorphism between these two fields, I hope that it is apparent that there is going to be an isomorphism, a very natural isomorphism, between the ring of polynomials over the field capital F and the ring of polynomials over the field capital F prime. Okay, these two are going to be isomorphic to one another as well. I hope that should be intuitively obvious to you. If these two fields are the same up to the fact that you've used different symbols, then when we generate the ring of polynomials over them, you're going to get an identical algebraic structure. How could you not? Okay, the only difference between these two is going to end up being symbols as well. Okay, so these two are going to end up being isomorphic. And just to make this absolutely crystal clear, let me state exactly how this isomorphism is going to work. Okay, so I claim there's a pi, there's mapping pi, which is an isomorphism between the ring of polynomials over the field capital F and the ring of polynomials over the field capital F prime here. Okay, so just to develop the intuition a little bit more, let me state this isomorphism explicitly. So if I've got some polynomial, which will be something of this form, the sum over I of ai x to the I, where all of these ai's, the coefficients of the polynomial, are from the field capital F, pi will map this onto the polynomial in the ring of polynomials over f prime here, which is the sum over I, and now the coefficient, we're just going to replace that with what it would be mapped onto by the isomorphism here, and I hope that's obvious. That's what you'd have come up with, I hope. Okay, so we're just going to have phi of ai xi. So I'm just taking any polynomial with coefficients in this field capital F and replacing the coefficients with what, if you rubbed them out and replaced them with what they should be in f prime according to this isomorphism, you would get. Okay, so I hope it is obvious that that is an isomorphism, and therefore I don't actually need to prove that pi obeys the axioms of an isomorphism. Of course you could prove that this is a bijective map, okay, that additive and multiplicative compatibility are all work, but I hope that that is intuitively obvious, that if these two are isomorphic, if those two are the same up to the fact that you've used different symbols, then if you generate the ring of polynomials over them, how could you possibly not get something that is only different because you've used different symbols? Okay, so these two algebraic structures are going to be equivalent. Okay, right, so we're still on the setup. This isn't the theorem yet, that's just a part of the setup, so this isn't my theorem. Okay, now what I'm going to take then is I'm going to take some polynomial p of x, which is in the ring of polynomials over the field capital F. Now of course this will have an equivalent polynomial in the ring of polynomials over the field capital F prime, and I'll call this p prime of x, okay, and that's just apply this isomorphism pi to the polynomial p of x, so I might just write this underneath. This is pi of p of x. Okay, replace all the coefficients of the polynomial p of x with what they are in f prime, what they're being mapped onto by this isomorphism phi here. Okay, and that will be some polynomial, the corresponding polynomial to this one in the ring of polynomials over the field f prime. Okay, so now you might be starting to predict what the actual theorem is going to be, where we're heading with this. Okay, so I've got two polynomials, the two corresponding polynomials, p of x in the ring of polynomials over the field capital F, and its corresponding polynomial p prime in the ring of polynomials over f prime. So now, what am I going to do? Of course, I'm going to construct the splitting field for p of x over the field capital F, and we'll call that capital K. So capital K is going to be a field extension of f, and in particular, it's going to be the splitting field for this polynomial p of x here. Okay, and in fact I might underline all of this in green, so all of this is in green. This is the field capital F, here's the polynomial, and now we've got the splitting field. And now we're going to do the same thing over here for f prime. So we've got f prime, here's the polynomial p prime, and we're now going to generate the splitting field for p prime over f prime, and of course we'll call that k prime. So k prime is going to be the splitting field for p prime over f prime, so it's going to be a field extension of f prime, and I'll highlight that in orange. So we're finished with the setup now. Now I can actually put the great claim of this theorem, and hopefully you should be able to anticipate exactly what I'm about to write here. Okay, so the claim is that the splitting field K is going to be isomorphic to the splitting field K prime. So K is going to be isomorphic to K prime. In particular, there's going to exist an isomorphism between them, which I'll call capital Phi, okay, which will be a mapping from K into K prime. Okay, and in particular, if I restrict this mapping Phi down to the field F, which of course is a subfield of capital K, K is the splitting field for P of X over F, so if I restrict capital Phi down to F, the mapping is exactly the same as little phi. Okay, so this isomorphism, when restricted down to F, is just the isomorphism Phi from F to F prime, so of course F is a subfield of K and F prime is a subfield of K prime. Okay, so I'll highlight all of that in red. This is the claim. K is isomorphic to K prime. Okay, the splitting field for P of X over the field capital F is isomorphic to the splitting field for the corresponding polynomial P prime over F prime. Okay, right. And of course, hopefully you can now appreciate that if I prove this, I will have proven that indeed the splitting field must be unique, because just let F prime equal F and let this isomorphism equal the identity map, which maps all of the elements of the field onto themselves, okay, then this statement becomes that if you have the polynomial, well, P prime now will be the same polynomial because the isomorphism is just the identity map, so P prime will be P, and now it just becomes that if we have these two splitting fields, K and K prime, they're isomorphic to one another. So this is exactly the uniqueness thing that we wanted to prove. Okay, so if we prove this, it will prove that splitting fields are unique, so we are entitled to talk about the splitting field of a polynomial over a field, capital F. Okay, right, so let's begin then with the proof of this theorem, and we're going to use the same sort of tactics as we used in the proof of the existence. In particular, we are going to do another proof by induction, and again we're going to be inducting on the degree of the polynomial. Okay, so proof, not of induction, proof by induction. Okay, right, so we will start off then with the initial case, which is the case where the degree of the polynomial, the degree of P of X, is equal to 1, and then we'll do the assumptive step and then the inductive step. Okay, so proof by induction, so the initial bit then. Okay, so we'll start off then with the case that the degree, and I'm making all sorts of spelling mistakes now, the degree of the polynomial P of X, is because the weather's so hot, I'll blame it on the weather. Okay, so the degree of the polynomial P of X is equal to 1 is going to be our starting point. Okay, so we want to prove that the theorem is true when the degree of the polynomial is equal to 1. Now, if the degree of the polynomial is equal to 1, then hopefully you appreciate that the degree of the corresponding polynomial P prime of X is also going to equal 1. Okay, all of the coefficients in here will just be mapped onto their equivalent element in F prime, and you'll end up with P prime of X also having degree 1. And note, because it's an isomorphism between these two, okay, you can be sure that if the coefficient, the leading coefficient in front of the x to the power of 1 term was non-zero here, the leading coefficient of P prime of X will not be equal to 0, okay, because remember, an isomorphism will map 0 onto 0, okay, so if the coefficient here was not 0 in front of the x to the power of 1 term, then it won't be 0 here, so the degree of the polynomial will remain the same. Okay, and all the 0 coefficients will obviously go to 0, so truly the degree of the polynomial will not be changed by an isomorphism in this way. Okay, right, so both P of X in the ring of polynomials over F of X and P prime of X in the ring of polynomials over F prime, both of them will have degree 1. Now we know that if we have a polynomial of degree 1 and we're generating splitting fields for those polynomials, well, we don't need to bother. The splitting field is just the initial field, okay, because these polynomials are already written in their degree 1 factorization in the ring of polynomials over the current field. So I can conclude, therefore, that K, the splitting field for P of X over the field F, is just equal to F. And I can conclude that K prime, the splitting field for P prime of X over F prime, is just equal to F prime. Okay, and therefore clearly the theorem is actually going to be true because I already know that f and f prime are isomorphic to one another. Okay, so remember what we're trying to prove is that k and k prime are isomorphic to one another. If k is equal to f and k prime is equal to f prime, then clearly k is isomorphic to k prime because f was isomorphic to f prime. Okay, and of course the isomorphism capital phi in this case will just be the smallest isomorphism, well, the smaller isomorphism lowercase phi. Okay, so that's very easy. The initial step is very, very easy. Now we'll do the assumption step. So we will assume that the theorem is true. Okay, so assume true for the degree of the polynomial. So for the degree of the polynomial p of x is strictly less than n. Okay, so we will assume that provided that the polynomial has degrees strictly less than n, then it is true that if you generate the splitting field for this polynomial and its corresponding polynomial p prime of x, okay, so you generate k, the splitting field for p of x over f, and k prime, the splitting field for p prime of x over f prime, that the two are isomorphic to one another. So that's the assumption that we're making now. And now what we need to prove, the inductive step now, is that it's going to be true if the degree of the polynomial is equal to n. Okay, so to show that it's true, and I'll just put a little code on there, true for the degree of the polynomial is equal to n. And of course if we have done that, then we will be able to conclude that it's true for the degree of the polynomial is equal to 2 because it was true it was true when the degree of the polynomial was less than 2, which the only case you need to prove that for is 1, and then you'll be able to go up to 3 because if it was true for 1 and 2 it'll then be true for 3, and if it's true for 1, 2 and 3 you'll be able to conclude that it's true for 4, etc. Okay, the normal way that a proof by induction works. Okay, so we now want to show that it's going to be true for the degree of the polynomial is equal to n. Okay, now, just before we begin that then, I'd like to take a break here because of the high temperatures. I was losing the will to live by the end of the previous video, so I've renounced to take breaks more often. Okay, so we will have a break here, and in the next video we will prove that if we've got this assumption that it's true for the degree of the polynomial of x is less than n, then it will also be true for the degree of the polynomial is equal to n.